think we're all here. Looks like, no, we're not. We've got 4 people missing, but we're still going to get started anyway. Okay, goal today is to finish off implicit differentiation, which is what you need for your next test. And I want to get started at least on the intro part to the next section, even although that won't be part of your homework or the test. Okay, so let's get right into it. I'm just picking this one as just an example of a really awkward version of implicit differentiation. So we've got square root of x add y, and over here we've got much nicer x plus y squared. This fella here will have to be written as a half power, because if I'm going to differentiate anything, I need a half power. So here goes. You get 1/2 x plus y to the negative a half times the derivative of what's inside. And x gets you 1 and the y gets you dy by dx. So essentially this is a chain rule. It's a half something to the negative a half times the derivative of the something. And the something, which is this, has a derivative, which is that. This fella just gets you 3x squared, and this fella gets you 3y squared dy by dx. I think you've noticed that when we did these later questions, they are downright ugly. They just are messy. They've got stuff all over the place. And we haven't even really started figuring out how to get dy by dx because there's so much other stuff going on. And it's really quite messy. So I'm trying to think, because there's at least 2 ways my brain is working right now. My first way is just to leave that alone and distribute it and then figure out what the answer is later. And my second thought is maybe I should get rid of this in some way. And that might make the answer prettier later. So it's either try and make it pretty now or try and make it pretty later. So I'm going to go for, yep, I'm going to rewrite this guy as that guy.
Is that a 1 on the top?
Yes, that's a 1. Okay. So I took this guy and wrote him down. I took this fella and called him 2, and a half power in the bottom is that. So basically this left-hand side can also be written like that. And then I'm going to do an over 1. I'm going to do a cross multiply. So what that gets me is this fella. And then I have 3x squared plus 3y squared dy by dx times 2 of these guys. And that was only to do one job. That was to figure out how to make that disappear. And now at least I don't have fractions. So that was worthwhile. If I'd went the other road, I would still have to have taken care of these fractional powers of x add y, and it would have just been as ugly, if not uglier. What do you think I'm going to do next? Remember, the eventual goal is to get dy by dx on its own.
Distribute.
That's what I would do. And do not talk yourself out of the answer because it looks, oops, 3 times 2 is 6, because it looks so horrendously bad. Right, so that times 2 root xy, this times 2 root xy, and 2 and 3 get you 6. Okay, we about 3 lines away, we'll have this thing finished. Give me another step. Give me something to do now. Remember, our ultimate goal is to get dy by dx on its own. Give me something I could do that would get closer to that.
Wait, for that line, how'd you get to get 6y squared square root y x plus y, you multiplied 3x squared times 2 square root x plus y, right?
Yes.
Okay, so why wouldn't you multiply 2 square root x plus y
Oh,
times 3x squared?
thank you. Just a mistake.
Okay.
Okay. Fix that mistake. But what do you do next?
Subtract the variable that has dy dx from both sides so that it's on the so it's all on one side with dy dx.
Okay, so from here and you right, subtract that guy to get him over here. While I'm at it, maybe I should subtract this to get it over there. All right. So I'll subtract terms that I don't like from both sides. So I don't like that one there, so I'll subtract it. I don't like the dy by dx here, so I shall subtract it. Okay, we're 2 lines off the answer. What do I do next?
Factor out a dy by dx.
Yeah. Have you noticed that you tend to finish with the same 2 lines? Right, one of them is factor out the dy by dx. Okay, we are 1 line off the answer now, just 1 more line and it's done. What do I do to finish?
Divide by the side or the expression.
Yeah, divide by the ugly guy on the right hand side. Have you noticed that it never got really nice? Wasn't it ugly to start with, and it's just as ugly when it's finished? There isn't any style points or factoring or anything going on in this one. Some questions are like that, right? You get nothing out of them. Now, that is not the only approach to that question. And this one works, and it is correct. I'm going to show you. Well, I'll talk about one technique and show you another. See, when I got to this line here, I could have just distributed this. Then I could have, subtracted things from both sides. And then I could have done the divide and done all the other things. The answer I would have got wouldn't quite look like this one, although it would be equivalent. The answer I would have got would have had x plus y to the negative a half in it, which would have eventually turned into a 1 over square of x plus y. So the answer I would have got would be equivalent to this, but much uglier looking. And then I'm going to use a rule I call, just because you can doesn't mean you should. Now that was the original question. Agreed? And I'm looking at that question and I'm saying, I don't like square roots. I already have proved it. Would you agree square roots do not play well with this process? They give you really ugly answers. Agreed? So I am now going to show you a different way of approaching this question, which will not look like this guy, but will be equivalent to him. In other words, it's the same answer, but in a different looking form. What do you think I'm going to do to both sides to make that question no longer have a square root? You said it, Robin, again.
Square it.
Square it. Would you agree that that one would be much easier to solve, to differentiate? Agree? No square roots, just normal powers. I mean, the only awkward one would be here. You'd have to do a little product rule. But would you agree that would be a lot less work? So if someone gives you a question like, different question now. And they ask you to, find its derivative. If I stuck to the order that it's in, wouldn't this be a quotient rule? Can you remember how ugly the quotient rule was yesterday? It was not a good place to be. Or turn it into that and do that. Would you agree that would be a much easier implicit differentiation to do? So just because it's written as an ugly square root, or it's written as a really messy looking fraction, does not mean that you have to do it that way. See, a little bit of algebra could turn it into something nicer. A little bit of algebra could turn it into something much more manageable. And the answer would almost always be prettier than it would be if you left it as a square root. Oh God, look at that. I still cringe at it, right? Or if you left it in this format, because that would be a pretty ugly answer as well. Are we cool with that idea? So if there's a chance, probably there won't be, but now and again you'll get lucky. Do the alternate version. It will make your life easier. Of course, I can't guarantee that WebAssign is clever enough to do all the permutations of a function that you produce. But if you do it correctly and tell me about it, I will check it. And if it's good, I'll just fix the homework grade and give you the points. So what is left? The only thing we are left to do is find the equation of tangent lines. To an implicit. Expression. I don't want to say implicit function because technically it's not a function. So let me find one. Where the heck are they hiding? I didn't do one. That was bad of me. Too late now. Okay, I'll just make one up. It's not hard to do. Okay. This is the standard question, right? Find the equation of the tangent line to the curve x cubed plus y squared plus 2x equals at the point 1, 2. So that's 1, that's 4, that's 5, 6. There we go. So find the equation to tangent line to some implicit function at the point 1, 2. Right, we've done enough equation of tangent lines to curves, so I wanted to throw this one in as an example. To know the process, isn't the first step going to be differentiate and find out what the slope of the tangent line at this point is, right? And then the second part would be the y minus y1 guy, right? Not going to change that. Let's find the derivative. 3x squared, 2y dy by dx, plus 2 equals 0. Take away 3x squared from both sides, take away 2 from both sides. Divide both sides by 2y. So I found the derivative. Now what do I do? Well, I'm going to find the slope of the tangent line. It's the value of this derivative at that point. So what do? I just plug x is 1 and y is 2. So I get -3 times 1 squared, take away 2, divided by 2 lots of 2. So let's see what that gets me. That gets me -5 quarters. Are you happy about how I found the slope of the tangent line at this point? Have you noticed that the only real difference is that I use the x and y values, where typically you would just use the x coordinate? So this is the derivative at that particular x and y combination. You get -5/4. And then you do y take away y1 equals m x take away x1.
Professor, I had a question.
Yeah. Go for it.
What happened to the 6 at the very beginning? How did it turn?
Oh, the derivative of the number 6 is 0.
Oh, okay, yeah, that makes sense.
No, I don't mind. I like questions.
It's hard to remember that. So I think problem 13, 14, and 15 are all going to be implicit find the tangent lines because they have points at the end.
Oh, I can see what happened. I got the wrong picture of them. Yes, they are. Yeah. So the questions that do this are 13, 14, and 15. Good. Right. Continue with this fellow then. It's going to be -5/4 x take away 1. So I have -5/4, add 5/4. If you add 2, which is the same as adding 8/4, you get that answer. Okay, I'm going to try something here. I'm going to see if it's going to work, of course. No guarantees. Just bear with me for a few moments. I'm finding Desmos. Okay, here's Desmos. Right, move Desmos over here. Fingers crossed. I am going to do Desmos and see whether or not it can actually work with implicit. So if it doesn't, well, I'm sure there's a way of making it happen. I just don't know it. So the original question was x^3 plus a y² and plus a 2x equals 6. Come on. Oh, Desmos is good. Hey, it draws implicit. Cool. You see the red? Looks something like say. And then I'm going to write my equation of my tangent line, which is y equals -5/4 x. Oh, I forgot the next. -5/4 x. So let's do that. -5/4 x plus 13/4, right? Ooh, did I screw up? I screwed up. At the point 1, 2, which should be here.
If you click it, it should tell you.
But it's not a tangent line.
No, it should tell you what the point is if you click on the line.
At the point, well, I'm trying to. Well, that's definitely the point 1, 2, but it's not on the curve. So
Is just looking at like if 0.12 was in the expression, wouldn't it be equals 7? Or am I?
There, I have fixed the question. I wrote the whole question down. Oh, that was
God, I'm unmuted.
that was cool. I would never have guessed that was my mistake. My math was perfect. My question wasn't suiting it because I gave the wrong implicit curve. But that was very observant, right? This guy here has to be 7 because if you use the numbers 1 and 2 and you put it in here, it's 1 plus 4 plus 2, which is 7. Evidently, 1 plus 4 plus 2 is 6 in my world. So that's where the mistake was. So if you imagine that was the original curve, which it is, when you plug it in, oh, by the way, because that's 7 or 6, do you notice that the math never changed? So I'll get kind of lucky there, right? When you put that in, you get to see all the 2 curves. And there is a perfect match. Right there. Isn't that a cool thing? That calculus, when you do it right, at least tells you the right answer. Okay, let's continue now. I wonder if I need to do any more. Let me close it for a minute. I guess I do need to do one more. Okay, last version of that question is going to be number 15. So the reason I've kind of changed my mind and decided to do this question is because we haven't as yet dealt with an expression that looked like this. In particular, we're being asked to find the equation of the tangent line at that awkward number, but just the point of how do you do implicit differentiation with fractional powers? I should have covered that. So power rule, no big deal. Power rule, remember to finish with the dy by dx. And what's the derivative of the number 4 going to get me then?
0.
Just a 0. I'm going to have 2/3 y to the negative 1/3 dy by dx. And I'm going to subtract that guy from both sides. So I have this. I'm then going to divide. And I'm going to be looking at a very ugly fraction situation, which I am not going to leave alone. I am going to fix it. Okay, this is the derivative in all its glory, and it is ugly times 2. Let's try and make it prettier. Give me any ideas of what you could do to this fraction here to make it nicer. One thing at a time is fine.
Multiply it by 3 on the top and the bottom.
Okay. Actually, that would work. I'm not going to do it, but that would work. Can do some even quicker than that, because it will eventually be what you said. Good. Light bulb on. What can we do here?
Cancel the 2/3.
Yes, just cancel the damn things. They're the same thing. The fact that they're fractions is a confusion, but not a problem. What Ethan was saying would totally work. I'm not saying that was a bad idea. It's a good idea. It's just, this is a little bit quicker, that's all. Okay. You know we don't like negative powers. Agreed? We just try and avoid them if it's at all possible. So can anyone figure out what to do with this x to the negative 1/3? And while we're at it, what to do with this y to the negative 1/3?
So since we have a negative power on the bottom, does that mean instead of going from the top to the bottom, does it go from the bottom to the top?
It does. And so it ends up there. And just like you said, the top to the bottom, it ends up there. And I just stuck the negative side out the rod. Would you agree it's getting prettier? mean, every time we do something, it's getting a little bit nicer. I don't know if you can see this one. I hope you can see what I'm about to do. Do you know that's a third and that's a third? I could just leave it alone because it's fine. But I'm going to do this. Because that looks kind of pretty. Are you okay with the third becoming a cube root, and a cube root of y over a cube root of x just becomes a cube root of y over x? That, to me, is as good as that's going to get. So the slope of the tangent line is going to be the value of this derivative at that point there. So I'll write the point down next to it. Okay, so it's going to be negative the cube root of the y value, which is 1. Oh, God in Himmel, why did you do this question? Would you look at that? We're going to have to get something nice out of that number. It's a cube root of 1 over negative 3 root 3. And somehow or other, that's going to end up being at least vaguely nice. It's actually not as bad as it looks. Okay, hold that thought. Let's just take care of it one step at a time. There's the negative at the side there, right? That's it out the road. Can I multiply this by root 3 upon root 3 to rationalize the denominator? Right. So I'm taking that guy, I'm going to multiply him by root 3 upon 3. That gets me root 3 on the top, and 3 times 3 gets me 9 on the bottom with a negative. Okay. Now I have a negative cube root of this guy. Oh. Change of plan. Saw a better way of doing it. 3 root 3 is actually 3 to the 3 halves. Right? 3 root 3 is 3 to the power of 3 halves. I'm going to stick that inside a cube root. Okay. These two negatives cancel out. Cube root can be done at the top and the bottom separately. The cube root of 1 is 1. What's the cube root of 3 to the power of 3 halves? It's actually not that bad. The cube root of 3 to the power of 3 halves.
Square root of 3.
Square root of 3. I can live with that. Would you agree 1 over square root of 3 is not that bad? I could live with it. So I'm just going to live with that. So we now know that the slope is that guy. And we've got the point with ugly coordinates. We have a slope of a tangent line, which is this guy. And then if we do y minus y1, we should be able to get the equation of the tangent line. Since this is the last question, I'm not surprised it is as ugly as it is. So the y goes there. Oh, take away a negative makes that a plus. So I have 1 over root 3x, this times this. Oh, that's not so bad. Compared to what that could have been, that is actually tolerable. I mean, it could easily have turned into a Frankenstein. If I'd went with my first plan, which is this plan, I don't think that question would have ended up looking so nice. I mean, I know it's going to be equivalent to that, but it'd be some I don't know, 6th power over square root monster that wouldn't look pretty at all. And that is the end of implicit. Any questions before we kind of talk about the intro to the next section, the one that's not in the homework now or in the test? Our next section, which is, let's get the number right, is up the top here, G6. I think it's logarithmic. Want to double check here. Make sure we are doing the right one. Bear with me. Because I know we have inverse trig to do as well. I think that comes after log, not before log.
On the homework, it says log and inverse trig.
So the book, this textbook has got them together. Right, so I'm cool. We can do the right, we're good. We can do the logarithmic thing. It's kind of funny that this textbook, normally they separate those two things because they have nothing to do with each other. It's not like logarithmic is helpful or used in the trig ones. Right. Let's start with the basics then. I would like to differentiate the log function, but I don't have a log function. It's not in my list. My list my list is quite small. I know how to differentiate powers. I know how to differentiate the 6 trig functions. And I know how to differentiate e to the x. But in none of those was the log ever mentioned. So we need to figure out what the answer is. And the derivative of the log is an answer that you probably wouldn't have expected. So that's magic, isn't it? If I just tell you the answer and you say, yeah, well, okay, you say this answer, I don't want to disbelieve you, but I'm not convinced. So just so that it's not magic, let's see if I can prove it to you, right? You don't need to prove it for an exam purpose, but just for peace of mind, wouldn't it be nice to know why it is what it is? Because it looks like it shouldn't be that answer. I'm not sure what the answer should be, but it shouldn't be that answer, right? It should be something else. So here's a pseudo proof. The natural log of x, ln of x, is actually the log to the base e of x if we're being pernickety, isn't it? Now, can you remember logs from 141, right? Natural logs were the most common logs. They're very useful things. And there was a thing I called the circle of life, which was how you could change a logarithmic form into an exponential form. Can you remember that algebraic process where expressions that use logs could be converted into expressions that used exponentials? And e to the power of y equals x. That's why I called it the circle of life, right? It's got a little circle going on. So what that is saying is that this is the same thing as that. Are you comfortable with that piece of algebra, even though it was 6 months ago and you kind of forgot it?
6 months. It's been longer.
Well, whatever that time period is. We're good with this so far, right? So what I'm going to now do is differentiate it. Well, I know how you differentiate e to the y. Isn't e to the y times dy by dx? And what's the derivative of x? It's a silly question, but I'm asking it anyway. What's the derivative of x?
1.
1. And now you divide both sides and you say, oh, but the answer you've got is 1 over e to the y, which is correct. But wait a minute, isn't e to the y equal to x? You happier now? That the derivative of a log, the natural log, is in fact 1 over x. Surprising, but nonetheless true. So in the big scheme of things, it's not the worst answer in the world. Did you agree remembering what? And you just have to remember it. You know, like you have to remember the derivative of a sine as a cosine, right? You can't keep always, you know, from scratch proving what the answer is because you've forgotten what it is, right? Just better to remember it. But at least you know it can be done. So how do you differentiate log functions? Well, we've done the first one, which is pretty much what you see is what you get. Now, suppose you get a log function like that, and I'd want to differentiate it. I think the key word here is chain rule. So if you want to differentiate this guy, 1 over the something times the derivative of the something. That seem reasonable? And suppose then you got, keep it simple, suppose you got that guy. I think the key word this time would be product rule. Agreed? Product rule. So let's mix and match the notation, use that notation as well. F dash J plus f of G dashed.
Wait, on the top equation, how'd you get 2x?
The derivative of x squared plus 1. So it's a log of something is 1 over the something times the derivative of the something. So I was using the chain rule.
Perfect, thank you.
And this one I'm using a product rule. So it's 1 times the natural log of x plus x times, and G dashed is 1 over x. And we end up with the answer, that guy. Actually not that ugly, agreed. Got a nice look to it. This question is an example of just because you can doesn't mean you should. Now, could I do that question as a Russian doll, chain rule inside a chain rule inside a chain rule? Yes, I could do it. Looking at how ugly that is, do you really want to do a chain rule inside a chain rule inside a chain rule? Most people would say, nope, don't want to go there. So sometimes, and this is one of the sometimes, there's an alternate. But to do this, I have to rewrite it in a format that's just going to be easier to do, right? Something that's the same as it, but easier to differentiate. And to do that, I'm going to have to take a little side note. There are 3 laws of logs. The first one says that if you have 2 logs, in this case to the same base, but 2 natural logs, the log of A plus a log of B is the same thing as the log of AB. Can you remember that? They're called the 3 laws of logs. They're basically the rules for how to add and subtract and multiply with logs. And in this case, the single log is A divided by B. Can you remember what the third one does? What's n times log of A? What does that one become? Last chance, anybody? Like 3 log A gets you this and 2 log A gets you that kind of thing. Right, n times log A gets you the log of E to the power of n. This one is the one that's going to help me with that. N can be anything, including a fraction. So I'm going to go back to this question and I'm going to write it as x squared plus 4x plus 1, but not as the cube root of this to the 8, but to the 8th third power. So you get a cube root of this as that guy. And then I'm going to use this law in that direction, which means that this fella can be written as 8/3 the natural log of that guy. And this guy is much easier to differentiate than that guy. Right? This is much easier. So its derivative, it's a chain rule, right? So it's 8/3 the log of somebody. So it's 8/3 over the somebody times the derivative of that somebody. And I guess if I wanted to make it pretty, I don't know if I can do much with this. It's what? 16/3 x, take away 32/3 over x squared minus 4x plus 1. And then I could probably pull out a 4/3. So there'd be a 4 here. Yeah, I can pull out a 16, even better. And that would leave me with, yikes, let's do it over here. If I pull out 16 on the top and 3 on the bottom, this is left with x minus 2, and this is left with x squared minus 4x plus 1. There's your answer. It's quite a nice answer, actually. So we've introduced a new guy, the log function.
Did you say that was the chain rule that we just did?
Yes, it was the log of a something. So from here to here is the chain rule.
The log of something.
Yeah, and chain rule, when it's not x, it's a chain rule. Well, that's definitely not x, right? That's x squared minus 4x plus 1. So if I see something that isn't, if it ain't an x, it's a chain rule. And that's how I recognized it was a chain rule. Here it's a log of ugly function. So the answer is 8/3, 1 over the something, times that bit there is the derivative of the something. And this line here becoming that line there was me just making it look pretty.